Hello students, welcome to my class of electrostatics. In the last class I discussed about some important points of electric potential, and also we have seen that what is the reference point one should choose to find out the electric potential. Now today I will discuss the potential of localized charge distribution. Now we have seen that potential of a point charge can be written like this, right? 1 by 4 pi epsilon naught q by r, and the reference point we have chosen at infinite distance, that means at infinity. Okay, so this is the potential for a point charge with respect to the infinite reference point. Now if there are collection of charges, then according to superposition principle we can write the potential at P point is like this, summation I to n qi by ri. So qi is this ith charge and ri is the distance from this ith charge to the P point. Okay, and suppose there are n number of charges are there. So in that case we have to apply the superposition principle and we can find out the potential. Now for continuous charge distribution, in that case this summation we have to replace with this integration, and this dq is an elemental charge inside a charge distribution. So the charge distribution can be volume charge distribution or line charge distribution or surface charge distribution. So if it is volume charge distribution, then the elemental charge, the dq, will be inside this volume charge distribution. If it is a line charge distribution, then it will be a small elemental length having charge dq. If it is a surface charge distribution, then in that case we have to consider a elemental surface area having the elemental charge dq. So for volume charge distribution, this dq we can write like this: rho, this tilted r prime, then d tau prime. Now you see this picture here, this tau prime is the elemental volume inside this charge distribution. Now O is the origin. So from the origin, the distance of this elemental volume where we are considering the charge dq charge is there, so the distance is tilted r prime, and from this origin the distance of the P point where we want to find out the potential, that is this tilted r, and this r is actually r tilted r minus tilted r prime, right? That we saw. So if you remember, I discussed this thing, this prime coordinate actually represents the source coordinate, source point coordinate, and this not prime coordinate is actually the field point coordinate. So field point means where we want to find out the potential, and source point means where our charge distribution is there. Okay, so this is rho tilted r prime d tau prime by r. Okay, this r is the distance from this elemental charge distribution to this P point. Okay, now for line surface charge, okay, so in that case this will be the surface charge density sigma, and for line charge distribution this will be lambda. Okay, so here what you have to remember that this reference point that we have chosen, it is at infinite. Okay, so here that is not written, but this is inbuilt that we are considering the reference point is at infinite point. Okay, so now let's take one example of the spherical charge distribution that we discussed in the last class in a different way, and we found out the form of the potential. Now here the starting point is this equation 1 by 4 pi epsilon naught integration sigma by r dA prime. So here the potential of uniformly charged spherical cell of radius r we want to find out, and we have to use this form of the potential. Okay, so this sigma is uniform over the surface of the spherical shell. Now this is a picture of that spherical shell, and this is the Cartesian coordinate, and here is the center. So the elemental surface is at on the surface of the spherical shell. So this is making angle theta prime with respect to this z axis. So we are in prime coordinate, so that we have to remember. So from this elemental surface, the distance of the P point is this r. Okay, so we can write the r square is basically capital R square plus z square minus 2rz cos theta prime. So this you can use by the vector addition concept, the triangle formula, right? So from there you can find out this r square equal to capital R square plus z square minus 2rz cos theta prime. Now here this r, instead of this r we have to put this form. So let's put that form. So now this is that form. Now what is this dA prime? So dA prime is an elemental area on the spherical surface. So I discussed in last few classes, one of the classes, that what will be the elemental surface area on a spherical surface. Okay, so today again I am showing that, again I am discussing that, because maybe you can forget that. So here this is that elemental area, this shaded portion. Now you can see this angle, it is making theta prime with respect to z, and this is the small angle, that is d theta prime. Okay, so in that case this length will be capital R d theta prime, right? So if this is that area, this is that area, I am talking about this length, this is R d theta prime. Now we have to find out this length. We know this length is r d theta prime. We have to find out this length, that is, what will be that? So for that, this length is r sin theta prime. Now if this is r sin theta prime, that means it is the, if we take the projection, this length will be same here on this xy plane, this one, r sin theta prime. Now this in xy plane, this is phi prime angle. So this small angle will be d phi prime. So in that case this length will be r sin theta prime d phi prime. So this length, this one is r sin theta prime d phi prime, and this we got r d theta prime. Okay, so this is a small rectangular shape. So what will be the form? This will be r d theta prime into r sin theta d phi prime. So we get this form, r square sin theta prime d theta prime d phi prime. Is it clear? Okay. Now this 4 pi epsilon naught I am multiplying here. Now we get this form. Now this r square is coming out, there is sigma will come out, and there will be 2 pi. 2 pi means this d phi prime, this is varying the angle d phi prime, which is in xy plane. So this is xy plane, this is z. So this phi is varying from 0 to 2 pi. So if you vary this d phi from 0 to 2 pi, 2 pi will come out, right? So that is actually that 2 pi. So our phi is varying from 0 to 2 pi, that's why this 2 pi is coming out. Now this is sin theta prime d theta prime, and you know this theta prime angle will vary from 0 to pi. So I told that if we vary the theta prime from 0 to pi and phi prime, if we vary from 0 to 2 pi, I can form a total sphere. Okay, so that's why the limit is from 0 to pi. Now after integration, this 1 by rz will come out, and this will be root over r square plus z square minus 2 rz cos theta prime, and 0 to pi we have to put. Now if we put that, we get this form, and this will be r plus z whole square minus root over r minus z whole square. Okay, so now if our field point is outside the spherical cell, that means we want to find out the potential outside the spherical cell and also inside the spherical cell. Now if it is outside the spherical cell, then in that case this root over r minus z square we have to put z minus r, because z is greater than r. We are considering the point, field point is outside of the spherical cell, so z will be higher compared to the radius of the sphere. But for points, if we want to find out the potential at a point which is inside the spherical cell, in that case this root over r minus z square, that will be r minus z, because r is greater than z, right? So for outside point, this we have to put z minus r. So from here we have to put, so this will be r plus z, and we are getting this form r square sigma by epsilon 0 z at outside point, and inside point this will be r sigma by epsilon naught. Now in terms of total charge on the cell, if we consider q is the total charge and sigma is the uniform surface charge density, then we can write q is 4 pi capital R square sigma. This is the surface area of the spherical cell. Okay, so if we put it, so here if you multiply 4 pi and below also 4 pi, then 4 pi R square sigma, that is q. So we are getting this form at outside point of the potential. And at inside point, again we have to multiply 4 pi r in the numerator and 4 pi r in the denominator, then it will be q by 4 pi epsilon naught r. So that this is the form at the inside point of the spherical cell. Now in general, we can write outside point, the form of the potential is like this: q by r types, q by small r if I tell, and inside the form of the potential is q by capital R type. So that means the potential inside the spherical cell is constant, and the value is same as the potential on the surface of the spherical cell. So this form actually we calculated in the last class, and the concept was little bit different from the fundamental point of view. Q infinity to r, the q by r. So in that case we get this form, right? Now today here I discussed from the charge distribution concept, and this is the form. This is similar to that. Okay. Now if you want to find out the potential for a linear charge distribution, in that case you have to consider this form. If you want to find out the potential due to a volume charge distribution, volume spherical charge distribution, then in that case you have to consider this form. So depending upon the form you have to do this. Even if you want to find out the potential due to a this kind of charge distribution, that is a surface charge distribution, in that case you have to find out this. So different case you can handle with these three types of form of the distribution, charge distribution. Okay. Now I will discuss the two equation, which is Poisson's equation and Laplace equation. Now we know the important properties of electric field, that is the del dot E, divergence E equal to rho by epsilon naught, and you know this is the differential form of Gauss's law. And another important property is curl of electric field is 0, because you know electric field is conservative field. So if curl of any vector field is 0, that vector field can be written as gradient of another scalar field. This is one vector identity. And here electric field we can write gradient of potential. Now why this minus sign is coming? because you know that the equipotential surface, all equipotential surface, so from suppose charge is there, and if you radially go outward, then the potential, the equipotential surfaces are spherical in nature, and the value of those potential will decrease if you go further. But the direction of the electric field is along radially outward. So that's why the minus sign is there, because gradient of any scalar field means that the space rate of increase of any scalar field. So here the del of V is actually space rate of increase of potential, and that is what is the direction? Direction is from outside to inside, means outside point to near point of the charge, but electric field is opposite to that direction. Okay, so that's why this minus sign is coming, and as I told, this is the vector identity. Curl of any gradient of any scalar field is 0. That can be easily proved from the fundament by the equation of gradient and divergence, a curl and divergence, curl and gradient. Okay, now so here E is minus gradient of V. So instead of this E here, we are writing divergence minus grad V, that is rho by epsilon naught. So minus del square V equal to rho by epsilon naught. So del square V equal to minus rho by epsilon naught. So this equation is called Poisson's equation. And if suppose there is one region where there is no charge distribution, so in that case this form will be del square V equal to 0, and this equation is called Laplace equation. Now there is some important importance of these equations, because what is the importance? Importance is, see here, if we know the potential, by this equation we can find out rho, right? We can find out the unknown charge distribution. And suppose we are in a region where there is no charge distribution, and using this Laplace equation we can find out the unknown potential. And even if we know the charge distribution, and if we solve the second order differential equation, then we can find out V. Okay, so del square means what? Del square is the Laplacian operator. This operator is called Laplacian operator, and in Cartesian coordinate the form is del square x square plus del square y square plus del square del z square. Okay, so this is a Cartesian form. In spherical polar coordinate there will be r theta phi component. In the next class I will discuss some points about this Poisson's equation and Laplace equation, how to solve a Laplace equation. Right, we want to find out the potential in a charge free region. What will be the form, what will be the form of the potential in one dimension, in 3 dimension, if we consider there is spherical symmetry. So if the charge is spherical symmetry, charge distribution, in that case what will be the form of the potential? So that thing we can do, so that I can do in the later classes. Okay, so these are the importance that we can find out the unknown potential from using this equation, and if we want to find out the electric field, we have to use this gradient of the potential form, this equation minus grad of this potential. So here we have to handle only one equation. Okay, but for the electric field we have to handle this equation minus grad V. Also we have to check whether that electric field, whatever we have found out, that is satisfying this condition or not. If it is not satisfying, then this formula is not valid. Okay, so in that case these two we have to check. But for this equation, this is a single equation that we have to handle, and we can find out the potential. If we know the charge distribution, if we know the potential, we can find out the unknown charge distribution. So as a whole, the whole picture is in this simple figure. So there is the relation, this is the relation between the potential and the charge distribution, del square V equal to minus rho by epsilon naught. So if we know the potential, we can find out rho, and if we know the rho, in that case we have to do this integration to find out the potential. Now here the relation between the potential and the electric field is E equal to minus grad V. So if we know the potential, we can find out electric field using this gradient form. Now if we know the electric field, then if we do this integration minus one reference point to the point where we want to find out the potential, so the limit of this integration will be like that, and then it will be E dot dl. So V equal to minus integration E dot dl. Now if we know the electric field, then to find out the charge distribution, we have to use this differential form of the Gauss's law, and also we have to verify whether this conservativeness of the electric field is satisfied or not. If we know the charge distribution, then we can find out the electric field like this. But here one thing we have to remember, this charge distribution has to be very much symmetric, otherwise it is difficult to solve this integration. So in that case, what we have to do? In that case, we have to do this. We have to find out the potential, and we have to use this Poisson's equation to find out the charge distribution. Okay, and if the charge distribution is known to you, then we can find out the electric field easily, right? So this all are interrelated, rho, V and E. Which one you want and how difficult you are facing, depending upon that you will use those formulas that you have to remember when you are dealing with electrostatic equations. You have charge distribution, you have potential, you have electric field. So whichever is known, from there you can reach to another parameter, and depending upon the symmetry. Okay, so today I am ending here. In the next class I will discuss the electrostatic boundary condition. What is electrostatic boundary condition? Okay, thank you.